All right, so we said that, let's see, we were figuring out polarity of molecules.
Right.
Now, since we spent so much time figuring out the polarity, general polarity molecules, now I'm expecting you to kind of remember some of those things and start to get a grasp of when you look at a formula, you can put, in some formulas anyway, you can pretty much quickly tell, okay, that's kind of polar, that's not polar.
Mm-hmm.
All right? We actually looked at methane in that earlier unit. Okay? And we said even though there's a polarity between these atoms, because those atoms are equally spaced in a what kind of arrangement? Tetrahedral. 4 atoms around a central atom gives you the tetrahedral. Evenly spaced, whatever polarity there is between those bonds is basically evened out all the way around. And so it's a nonpolar molecule. Okay? So this is nonpolar. All right? It's a really small molecule. That makes sense? Really small. Okay? You'd have to be a noble gas to be smaller, probably. So, what's the likelihood this is going to be a solid? I'm actually asking questions of everybody in the class over there, guys.
Very likely.
That's you, huh? Very small. What kind of conditions, looking at that Venn diagram from earlier, what kind of conditions will we have to get something like this to be a solid?
Bigger size and shape particles.
Well, we can't make it bigger. We're going to stick with that same size right there. Huh?
Temperature.
Really, really low temperature.
Yeah.
Or also really, really high pressures. Okay? If we force them together with enough pressure, we still have to have the temperature way down. But we can, the pressure temperature thing might make it be a solid. Okay? But you almost can't find methane in a solid form. All right? Let's see, what is it? The planet? No, it's not a planet anymore. Pluto.
Oh, it's a dwarf planet.
Yeah. Okay?
Still a planet.
On the planet Pluto, there's a good deal of methane. And the planet Pluto has an egg-shaped orbit around the sun. Okay? When it comes closer to the sun, the methane becomes a gas. And Pluto has an atmosphere of methane. When it's out on the outer reaches of that egg-shaped, at least that's the theory anyway, the egg-shaped orbit, it gets even colder. It's further away from the sun. The methane freezes.
So we probably couldn't live there.
You couldn't live there, not and breathe on it anyway, no.
What do we have like? What are those things called? It was in the lab thing.
Yeah, well, let's not worry about that right now. Okay, you could have. I suppose you could create a spaceship that could park itself on there, and you have your own atmosphere and everything. But
Goodyear tires.
why would you want to do that? Okay. All right.
What if we run out of
Okay.
methane?
Let's think about this now. Let's look at something like this. All right, now you got to use your brain here a minute. You got to think imaginatively. All right?
Oh, I left it at home.
Okay. If we were to draw the complete structural drawing of this, what runs down the center? Carbons. What surrounds those carbons? Hydrogens. So it's completely surrounded by hydrogens, but the carbons run down the center. Is this going to be a polar or non-polar molecule? Non-polar for the same reason. Even though it's a longer string of carbons, there's still that even spacing of hydrogens all the way around. Okay? I mean, you'll have to take college organic chemistry probably before you actually fully understand this. You just have to kind of imagine that those hydrogens are spacing themselves around. Remember, you got this VSEPR theory, VSEPR, where the electron pairs that are shared are being repulsed, and so they try to arrange themselves, those bonds try to arrange themselves as far apart as possible around that central atom or the series of central atoms here, such that those hydrogens are completely surrounding that whole chain of carbons. And if this is nonpolar, this is going to be nonpolar for the same reason. Okay, so it's nonpolar. All right. Now, which one of these is more likely to be a liquid at room temperature and pressure? This one or this one? The pentane. Because of what? The size. And what is the size doing that causes that? It's not just because it's bigger. There's something else going on inside that electron cloud that's causing this. The random movement of electrons that gives you more space for that temporary polarity. Okay? So those temporary dipoles have more of an effect in a long molecule. Alright? Does that make sense? Okay? So because we have more, a larger molecule, and especially because of the way it's shaped, this is kind of a long, thin, or wiggly molecule, kind of like a worm. Alright? Because it's stretched out like that, there's more surface space for those molecules to actually bump up against each other. And that allows more places along there for that temporary polarity to actually affect them being drawn and stuck together. So there's some stickiness there. This has more tendency to be a liquid. And in fact, we would probably classify this as a liquid at room temperature and pressure. Okay? Which one of these is easier to turn into a solid? The pentane, sure. Okay? It has a much higher melting temperature and boiling temperature. Okay? How would you know that? Well, let's think about it. What is temperature doing? It's making the molecules move randomly faster or slower. Okay? Well, if we cool both of these down because of the stickiness of this molecule, which one of these is going to freeze at the higher temperature? Which one freezes at the higher temperature? In other words, if they're starting out at room temperature, you're freezing them down at the same rate. Which one freezes first? Pentane. That makes sense? Yeah. Has a higher melting temperature. Okay. And if they're both, which one is going to, if they're both gases, which one is going to condense into a liquid first? Pentane. So it has a higher boiling temperature. Okay. That makes sense? Yes, sir. We stretching your mind a little bit? Yeah. Some of you going,
my mind's like,
yeah. Good. Well, again, you've got to be able to use your imagination to kind of figure out what's happening here. I mean, you don't have to, but I want you to do well on the next test. Okay? So you've got to use your imagination. Sometimes you just close your eyes and imagine what's happening. All these factors are coming into play. And you've got to keep all these factors in mind. Okay? Strength of attraction between particles, size and shape of particles, how fast the particles are moving. Okay? Does that make some sense? Mm-hmm. All right, now let's add another factor here. Oh, wow. We said that water is a highly polar molecule, right? Yes. Because the oxygen is far more electronegative than the hydrogen is, and it's bent. Okay? So we got a partially negative end here and a partially positive end over on this side. All right, let's replace one of these hydrogens with one of our methyl groups. So we got a CH3, which is kind of nonpolar, and we're going to stick one of those O's and H's on there. Well, now we have this polar part of the molecule right here, don't we? Yeah. And we have this non-polar part of the molecule over here. And it's polar, non-polar. It is a little bit of both. This is a, what do we call these kind of formulas? What kind of things have this OH group on a carbon? What are they called?
Let me check my test references.
Alcohols. They're alcohols. Okay? And alcohols, all alcohols, have a partially nonpolar end and a partially positive end. Or a partially polar end, I'm sorry. So it's polar on one end and nonpolar on another. But this is methanol. Methanol. Okay? And so it is pretty polar because this thing's kind of small and, you know, there's kind of a balance between them. All right? Suppose I put two of these carbon groups together. Which one of these two, then, is more likely to be a gas and which one is more likely to be a liquid at room temperature and pressure?
Gas on top, liquid on bottom.
Yeah. Because... well, I don't know. Maybe not. Maybe not. Let's just look at it. Let's look at it for a minute. This part is the polar end.
Yeah.
And it's a much bigger effect over the whole thing than this one is.
Mm-hmm.
Okay? It's really kind of hard to tell with those. This is ethanol, that's methanol. They're both going to be liquids at room temperature and pressure. Okay? So if I have methanol and I compare it to ethane, this is a gas, and this is, for the most part, a liquid at room temperature and pressure, although it's very volatile. It easily becomes a gas. Okay? They're roughly the same size, roughly the same mass. Okay? This is going to be a liquid. Okay? This is going to be a liquid at room temperature and pressure. And this, which is roughly the same size, is going to be a gas. Liquid gas, because of this polar end. We've got a non-polar end over here and a polar end over here. Got that? And so the more the polar parts have an effect on the whole overall structure, the more of this attractiveness we have, this stickiness we have between these molecules. Okay? No, that's not right. There should be a 2 there. Okay, which one of these is likely to be a liquid at room temperature and pressure?
The top one.
Yeah, that one right there, because it's got a whole lot of polarity going on there, doesn't it? This is the stuff that's in your car radiator. Right here. Antifreeze is mostly this stuff right here.
What is it?
Huh?
Antifreeze?
It's called glycol. Okay, you can call it. It's a diol, which is two alcohols on there.
Yeah.
But when you put 2 alcohols right next to each other on adjacent carbons, it's called a glycol. You don't have to know that because we didn't cover that, but it's called It's called ethylene glycol. That's a common name for it, ethylene glycol.
Yeah.
Okay, and it's very polar, and it resists. It helps the water that's also in your radiator resist freezing. Okay. All right. So is that starting to make some sense to you?
Yeah.
Okay. Larger the molecules, the more likely they are to stick together, the more easily they become liquids or solids. Right. Smaller the molecule, more likely they are to be gases. Faster they're moving, more likely they are to be gases. The colder they are, more likely they are to be solids. The more polar they are, the more likely they are to be liquids or solids. The less polar, in fact, any attraction that draws them or makes them stick together more tends to make them more likely to be a liquid or solid than a gas. Does that make sense? So we've got a dynamic sort of system going on here.
Dynamic duo.
Well, not a dynamic duo. It's like a dynamic trio or a titanic trio. Okay? All right? We got 3 factors all at play at the same time and all affecting the organized structure of the material. Highly organized, those are solids. Okay? Highly disorganized,
Gosh, trying to learn.
those are gases. And so in the middle are those liquids.
Right.
Okay?
Yep. Alright, organized solid.
Highly disorganized. Organized yo.
That's all. I spelled it in a hurry. I was writing in a hurry. Highly disorganized.
Right, organized.
Okay? All right.
An R.
How we doing? Is your head spinning?
Can't arrows go back
No,
the
my head
other
was
way?
spinning. I'd be
Sure. Either way.
My neck was like broken or something.
Okay.
Can't they go towards the liquid?
Well, if it's a solid, it can go toward the liquid by increasing temperature.
Yeah. I
It-
just didn't know because arrows were only going one
Okay.
way.
Well, no, I mean, it can go either way like that. If you want to put a arrowhead there, I can.